Okay, let's talk about the last lab of this term, where it's substitution reaction, and we are going from a tertiary alcohol into a tertiary halide. Now, realize the first step here is going to be the same as you saw in case of elimination, in that the OH is going to get protonated. Chlorine, being a good leaving group, is going to leave, and that will give you the protonated alcohol. And so if you can guess whether the chlorine should attack or it should give you a carbocation or what, yep, you got it right. You should let the water go so that you end up with a tertiary carbocation. And now what's important to understand here is that the Cl is going to attack either from the top direction or from the bottom direction, so front or behind. And so you're going to end up with a racemic mixture, but both of those would be possible. And so your product is going to be, let's see the Cl pointing towards us, that's my Cl, and the Cl is pointing at the back, and the other. Together we call this a racemic mixture. Of course, in this case there is no chirality, so we don't have to worry about that. But realize why, if you compare this reaction to the reaction that you ran last week, why is it that you're not going to see a product in a substitution product in that case? Recall that in that situation we started our reaction with concentrated H3PO4 as the source of proton. And if you think about the steps as to how the reaction will take place, of course the protonation takes place, the biphosphate will leave OH2, positive charge, or ready to leave. So the intermediate is exactly the same thing. But now your H2PO4 is pretty bulky, and it has resonance. That negative charge is not really localized at one particular position, but rather it's spread over the entire unit, which means that this is a good base, but not a nucleophile. And so this is going to seek protons, but it is not going to attack at the carbocation. So you're not going to show the O negative attack at this positive center and give you a substitution product, but rather that one of the beta hydrogens rather, is going to attack. Electrons will move, and you're going to end up with the alkene. So that's what we saw last week. But this week we are going to focus on substitution, not elimination. Realize that the Cl negative is a good nucleophile. There's only one atom with the electron, so it is a good nucleophile. It's not too big. And in terms of a base, it's somewhat of a weak base or moderate base. So you're not going to see, the reason why I'm calling it a moderate base, by the way, is because the corresponding conjugate acid is very strong acid. So you can hopefully envision that you're not going to see a lot of elimination in that case. Realize either way, our substitution product is the chlorine at the tertiary location, and the byproduct in either case, whether it's elimination or substitution, either way it's water. So that's the reaction that we are going to run, and hopefully you understand why we did not see any substitution in the lab that we ran last week, but we will see substitution in this case. Now, if somebody wanted to check, you can always check and to find out, because substitution and elimination kind of go hand in hand. So there is a possibility that as you're running the substitution, a little bit of your material can go through elimination depending on reaction conditions. But we are trying to minimize that. That's the aim. But once in a while, there is a possibility that you might end up with an elimination, the same beta elimination product. And you could look up for that in the IR in the 1600 region, or you could do a KMNO4 test and it's going to cleave and that pink color is going to get discharged. If you see something in the IR, of course. However, if you don't see anything in the IR, you're just going to go with the substitution as your product, and we are going to take steps to characterize that. Now, first off, how are we going to run the reaction? It's a pretty straightforward setup. So what we are going to do is we are going to take an Erlenmeyer flask, and let this be the 50 milliliter Erlenmeyer flask. We are going to put in a stir bar. We are going to add 5 milliliters of the alcohol, and we are going to add to that 15 milliliters of concentrated HCl. Now this concoction is going to go in the Erlenmeyer flask, and we are going to let it stir at room temperature, and we are going to do this for about 10 minutes and see within 10 minutes whether we are able to get 2 layers or not. That's the aim. Now the product that you get that is nonpolar in nature or more nonpolar in nature, does not dissolve in water, and so you should be able to simply separate it out on the basis of density and the fact that it doesn't quite mix with water. So after 10 minutes, what we are going to do is we are going to sort of stop the stirring, and we will see if the 2 layers have formed, and we'll transfer it into a measuring cylinder, a 10 milliliter measuring cylinder, or rather 25 milliliter. So 20 to 25 milliliter measuring cylinder. I believe we have 25, so that's what we are going to go with. If we find 20 in the lab, we'll go with that. So hopefully you can see that all of the water is going to settle at the bottom, because it's not really water but rather a dilute HCl solution at this point of time, and your product is going to be up top. So what you're going to do is you're going to use your Barol pipette and transfer all of the product into a new flask, and to this we are going to add solid K2CO3. Now understand the reason why we want to use K2CO3. Your product has just seen concentrated HCl, and it's in the nature of bicarbonates and carbonates that they would react with HCl, go through a double replacement reaction, and they would generate CO2. So K2CO3 plus HCl is going to give you 2 KCl plus H2CO3, and this H2CO3 is going to spontaneously disproportionate into water and CO2, and that CO2 is the bubbling that you see. Now if you take real good care of separating out the product and your aqueous layer, you actually should not see any bubbling. So if you took real good care in separating the two out, it should be a clean separation, and it should only be a product which should be devoid of any HCl, and that would mean that there should not be any any HCl, and hence no carbon dioxide should be produced. At that point of time, if it looks very clear and it did not bubble, I would encourage that you should take the time to just go ahead and take an IR. If not, let's in your IR, if you would not have seen bubbling, so no bubbling, that means there was a clean separation. And that means that there would be no water and you should not see any peak at 3300. On the other hand, if you did see bubbling, if you saw some bubbling, then you will have to add calcium chloride as your desiccant, and you will then transfer this into a round bottom flask and subject that to a short path distillation. Again, the thermometer goes up to the point at that Y, and the receiver adapter over here, and then your receiver flask. So you're collecting your product, and give it some time. Give it time to cool down, because as you know, hot stuff absorbs moisture faster than cold stuff. And so if you basically dismantle your material real quick, what's going to happen, of course the stand is going to be there, what's going to happen is that it's going to absorb moisture from the atmosphere and it's going to become wet again, and you don't want that. So again, take extra care while you're transferring, because that will save you a lot of time in terms of additional steps to be taken to remove any water from your product. Now, once you have gotten your product, that would be then taken, because you would assume that this would be pure, and you would take the IR of that, the yield of that, and your chemical test as well. So there are three things to do. Again, if you don't see any bubbling, it's a clean separation, go ahead, do an IR. Sometimes though, we do see that the amount of water would be so itty bitty, or the bubbling, if you did not really quite catch it, the amount of water that would be generated would be very small, but the IR would be able to catch it, and so you will see the peaks for that, in which case you will have to do the distillation anyway. But in your conclusion, what we are seeking is, again, the IR, the percent yield, and the chemical test. Now, what is the chemical test? Let's talk about that. The chemical test is, let's take a look at what we had and what it has become. So we had an alcohol, and it has now become a chlorine derivative. It's in the nature of a tertiary halide that when you mix it with 1% silver nitrate, it's going to give you a white precipitate. So you should see a white precipitate when you mix 1% silver nitrate with your product. That would not happen in case of your starting material. Now realize that the alcohol and the silver nitrate might seem that they are forming two different layers. So you can absolutely add 2 to 3 drops of acetone, just the same way we did last week, to kind of homogenize and keep everything in one layer, and so we are seeing the reaction properly. And the presence of the white precipitate is basically your positive test. That would mean that you have the tertiary halide now in the system, and you were able to carry out the substitution process absolutely well. You would then take the IR. I would let you look for the peaks for the CCl bond. That's a new bond that has been formed. And of course, you will also calculate the percentage yield. The one thing you have to keep in mind is this time you have started with 5 milliliters of the starting material, not 5 grams. So you have to take the time to convert the milliliters into the grams and go from there. All right, see you in class.